Welcome to This Explainer. Today, we're diving straight into a completely fascinating journey, tracking how a quiet, almost unnoticeable spark out on the open ocean transforms into the devastating roar of a raging storm. We're going to break down the actual atmospheric physics behind literally one of the most powerful forces on planet Earth. Let's get right into it.
You know, these massive tropical cyclones impact millions of people across the globe every single year. They flatten infrastructure, unleash just immense floods, and can completely disrupt entire economies. But before a storm can unleash all that destruction, it actually has to be built. So the core question we really need to answer today is this: what exactly makes a typhoon form? Like, what specific atmospheric ingredients have to perfectly combine to give birth to a monster like this?
Okay, here's our roadmap for today. 1. The spark of formation. 2. Spin and intensification. 3. The eye and eyewall. 4. Tracks, landfall, and decay. And finally, 5. The climate change connection.
Part 1. The spark of formation. It all starts with warm ocean waters.
So, that initial spark, it's all about heat. Specifically, sea surface temperatures need to be sitting right around 26 to 27 degrees Celsius. That's roughly 79 degrees Fahrenheit for those of you using that scale. Without that exact temperature, a typhoon can't even begin to develop. You can kind of think of this warm ocean water as a massive liquid battery that's eventually going to power the entire storm. It is the absolute baseline threshold.
And here is exactly how that process kicks off. Step 1. The sun beats down and heats the ocean, which causes mass evaporation. Then, step 2, all that moist, warm air starts rising up into the atmosphere. Step 3. As it rises, it creates a significant low-pressure zone right down at the surface. And nature hates a vacuum, right? So finally, in step 4, cooler air immediately rushes in to fill that void. That new air gets heated, it rises too, and suddenly this whole cycle is accelerating, continuously driving that surface pressure lower and lower.
Which brings us to Part 2, spin and intensification. This is all about how the storm gains its incredible power.
Now we have to talk about a genuinely fascinating principle called the Coriolis effect. Remember how that cooler air is rushing straight inward toward our low-pressure center? Well, the Earth is simultaneously spinning right beneath it. The Coriolis effect is basically the physical deflection of that rushing wind caused by the Earth's rotation. So instead of flying in a straight line directly into the center, the air gets twisted. And that twist, that is exactly what sets the stage for the storm's massive, signature spinning motion.
And geographically, this plays out in some pretty wild ways. Because of the Earth's spherical shape and how it rotates, the Coriolis effect actually deflects wind totally differently depending on where you happen to be. In the northern hemisphere, these storms twist counterclockwise, but down in the southern hemisphere, they spin clockwise. It's literally planetary physics playing out right in front of us. Now, as this massive rotating system organizes itself, it actually graduates through a few distinct stages. It kicks off as a tropical depression. Then, if it manages to hit sustained wind speeds of 39 miles per hour, it officially becomes a tropical storm and actually earns a name. Once those winds ramp up to 74 miles per hour, well, that's when we have a full-fledged typhoon on our hands.
But you might be wondering, how does it accelerate from a mere depression to a 74-mile-per-hour monster? The absolute crucial ingredient here is latent heat. See, as all that rising moisture condenses into giant storm clouds high up in the atmosphere, it literally releases heat. This extra heat then warms the surrounding air, making it rise even faster, which in turn violently pulls more air from the surface even faster. Latent heat acts as this terrifying self-feeding engine that rapidly intensifies the storm, supercharging those wind speeds, especially when high-altitude wind shear is low.
Moving on to Part 3, the eye and eyewall. Let's take a look at the internal structure of this beast.
A mature typhoon is composed of two incredibly distinct regions. Right in the middle, you have the eye. This is a deceptively calm center where air is actually descending, which sometimes even brings clear, sunny skies. It's crazy because people often mistakenly think the storm is completely over when the eye passes over them. But directly surrounding this eerie calm is the eyewall. This is a violent, towering ring of thunderstorms containing the absolute most extreme winds of the entire system. When the backside of that eyewall hits, it brings the absolute worst impacts of the storm.
To really give you a sense of just how much sheer power we're talking about, let's look at a recent example from Met Office tracking data, Typhoon Regasa. At its absolute peak, churning near the Philippines and China, Regasa's central pressure plummeted to a staggering 905 millibars. To put that into perspective, in meteorology, lower pressure equals a much more intense storm. Hitting 905 millibars, that makes it an incredibly strong, exceptionally dangerous system packed with absolutely devastating eyewall winds.
Next up is Part 4, Tracks and Decay. Let's explore their paths and how they eventually dissipate. First off, just a really quick note on terminology. While we use the term typhoon specifically to talk about storms in the Northwest Pacific, the exact same atmospheric mechanics apply globally in very specific basins, usually between 5 and 30 degrees latitude. So, over in the Atlantic, we call them hurricanes. Down in the Indian and Southwest Pacific Oceans, they're known as cyclones. But honestly, no matter what name they go by, they all follow the exact same rules of life and death.
Out in the Pacific, typhoons typically track from east to west, mostly driven by prevailing easterly winds. These things can travel at speeds up to 30 miles per hour and cover an astonishing 3,000 miles. Think about that immense distance. As they travel, they frequently threaten coastal countries perfectly positioned in their path, places like Japan, Taiwan, and the Philippines, before they eventually start to veer northwards.
But hey, the engine can't run forever, right? A typhoon ultimately dies when it loses its primary fuel source. When the storm encounters cooler water, or when it finally makes landfall, that infinite supply of 27-degree ocean water gets totally cut off. The latent heat engine basically stalls out. The low-pressure system begins to unravel, and it degrades back into a tropical storm. Now, a quick warning, even in this decayed state, it is crucial to remember they can still dump immense, deadly amounts of rain, causing massive floods and landslides. And sometimes, if they move far enough north, they can even transform into massive extratropical storms, bringing severe weather well outside the tropics.
Finally, Part 5, the climate connection. This is a growing threat we absolutely need to understand. Because typhoons rely so heavily on warm water, geography matters immensely. The Philippines, for instance, sits right next to some of the absolute warmest waters in the entire Pacific Ocean. Because of this prime location, they experience an average of 20 storms every single year. This profound vulnerability was seen with devastating clarity back in 2013 with Typhoon Haiyan, a super typhoon that caused over $13 billion in damage.
And there is a very clear, direct correlation outlined by the Intergovernmental Panel on Climate Change. It's simple physics. Because typhoon formation relies entirely on sea surface temperatures, warmer oceans naturally lead to stronger storms. The data clearly points to an expected increase in massive Category 4 and 5 superstorms over the coming decades.
Understanding the true anatomy of a storm isn't just about nerding out over atmospheric physics. It is fundamentally about preparation. By knowing exactly how these storms form, how they intensify, and how they track, we can better anticipate the sheer force headed toward vulnerable coasts. So to wrap up this explainer, I want to leave you with a question to really ponder. As our oceans inevitably continue to hold more and more heat, how will global communities prioritize the climate adaptation and sustainable infrastructure needed to withstand the super typhoons of tomorrow? Thanks so much for learning with us today, and we'll see you in the next explainer.